Press your hands firmly against the desk or the chair beneath you. You feel the solid structure, the quiet stability of the room around you, and the comforting sensation that you are anchored in a steady, unmoving center. But that feeling is a complete illusion. The truth is that the physical ground is dragging you through a violently expanding void at incomprehensible speeds, trapped inside a star system that is merely a microscopic speck of dust drifting endlessly in the dark. Today, we will explore exactly how unbelievably small the Milky Way galaxy truly is, and why our seemingly immense home is nothing but an insignificant drop in an overwhelming cosmic ocean overflowing with countless other galaxies. We will confront the terrifying reality of the observable universe. Today, we answer the ultimate question: how unbelievably small is the Milky Way galaxy really? The truth is that the universe is an overwhelming structure expanding 93 billion light-years across and harboring 2 trillion galaxies. Against this incomprehensible scale, the Milky Way galaxy we consider so massive is reduced to a mere drop of water in a limitless ocean. You are not watching this alone. We are stepping into this cosmic expanse together. To help us keep these journeys alive, please subscribe to the channel and share your thoughts in the comments. But first, tell me, where exactly in the world are you watching this from, and what time is it there right now? Leave your location below, and now, let us begin our descent into the void. For the longest time in human history, when we looked up at the night sky, we believed that what we saw was the absolute limit of existence. We felt a deep sense of certainty that the glowing river of stars stretching across the dark canvas above us, our Milky Way, was the entirety of the cosmos. To truly understand how our perspective was shattered, we must travel back just over a century. The year was 1920. The setting was the prestigious Smithsonian National Museum of Natural History in Washington, District of Columbia. On the 26th of April, the great halls of the museum buzzed with intense academic anticipation. The greatest astronomical minds of the era had gathered to settle a fundamental dispute about the nature of reality itself. This event would go down in history as the Great Debate. Taking the stage to defend the reigning dogma was Harlow Shapley, a highly respected astronomer with the weight of the scientific establishment behind him. Shapley presented a vision of the universe that was both grand and comfortably bounded. He argued passionately that the universe was synonymous with the Milky Way galaxy. According to his extensive calculations, our cosmic home was an unimaginably massive disk, spanning an estimated 300,000 light-years in diameter. In Shapley's view, every single point of light, every glowing cloud of gas, and every distant spiral nebula we could observe through our telescopes was safely contained within the borders of the Milky Way. This was the undisputed truth of the era. It was a logical, cohesive, and deeply comforting model. The universe was vast, yes, but it was singular. It was ours. However, intellectual rebellions always begin with a small, persistent voice of doubt. That voice belonged to Heber Curtis, who stood opposite Shapley on that historic stage. Curtis challenged the establishment with a radical idea. He looked at the mysterious, faintly glowing spiral clouds scattered across the night sky, what astronomers called spiral nebulas, and suggested they were not merely gas clouds floating within our galaxy. Instead, Curtis argued that these structures were entirely independent island universes. He proposed that they were separate galaxies, existing far beyond the edges of the Milky Way. The debate raged on, fueled by conflicting measurements and the limits of early 20th century technology. Shapley leaned heavily on the accepted data of the time, which measured the rotational speeds of these spiral nebulas. According to those measurements, if these nebulas were truly as massive and distant as Curtis claimed, their outer edges would have to be spinning faster than the speed of light, a physical impossibility. Therefore, Shapley concluded they had to be relatively small local clouds of gas right here in our own galactic backyard. Curtis, on the other hand, pointed to the faint explosions of dying stars, known as novae, within the Andromeda Nebula. By comparing their dim appearances to similar explosions closer to home, he calculated that Andromeda had to be at least 500,000 light-years away. Despite Curtis's compelling arguments, the scientific jury of 1920 found Shapley's defense of the established dogma far more convincing. The data regarding rotational speed seemed unbreakable. The consensus held firm. The Milky Way was the entire universe. Curtis's island universes were dismissed as an interesting but ultimately flawed hypothesis. The boundary of reality remained firmly fixed at 300,000 light-years, but science does not care about consensus. It only cares about the truth hiding in the dark, waiting for a better lens to bring it into focus. That lens was being built high in the San Gabriel Mountains of California, at the Mount Wilson Observatory. There, housed inside a massive freezing dome, sat the Hooker telescope. With a primary mirror measuring a staggering 100 inches, 2.5 meters, across, it was a colossal feat of engineering and the most powerful observational tool humanity had ever constructed. On the freezing, isolated night of December 30th, 1924, a young astronomer named Edwin Hubble sat perched in the cramped freezing observer's cage high above the massive mirror. The air inside the dome was kept as cold as the outside winter air to prevent heat waves from distorting the precious incoming light. Hour after hour, Hubble manually guided the massive machinery, keeping the telescope locked onto a specific target in the deep sky, the spiral nebula in the constellation of Andromeda. Hubble was not looking at the nebula as a whole. He was hunting for a very specific type of star within it, a cosmic beacon known as a Cepheid variable. These stars are the metronomes of the universe. They pulse, growing brighter and dimmer in a highly predictable rhythm. A few years earlier, another brilliant astronomer, Henrietta Swan Leavitt, had discovered a direct relationship between how slowly a Cepheid pulses and its true intrinsic brightness. By measuring the time it took for the star to cycle from bright to dim, Hubble could determine exactly how much light it was actually emitting. Then, by comparing that true brightness to how faint the star appeared through his telescope, he could calculate its exact distance from Earth with unprecedented accuracy. That cold night, staring into the photographic plates exposed by the giant Hooker telescope, Hubble found his target. He identified a Cepheid variable, which he labelled V1, pulsing steadily in one of the outer arms of the Andromeda Nebula. He painstakingly recorded its rhythm. He crunched the numbers. He calculated the true brightness, measured the apparent dimness, and solved the equation for distance. When the final number emerged from the mathematics, it was not just a measurement, it was a hammer blow to the very foundation of human knowledge. The result was not a few thousand light-years, it was not even 100,000 light-years. The distance to the star Phi 1 in the Andromeda Nebula was calculated to be 900,000 light-years. Hubble stared at the number. The implications were staggering. According to the absolute, undisputed dogma championed by Harlow Shapley and accepted by the entire scientific world, the absolute edge of the universe was only 300,000 light-years away. Everything that existed was supposed to be neatly packed inside that boundary. Yet here was a star, unequivocally measured, sitting 3 times further away than the supposed edge of reality. If the established model of the universe was entirely correct, how could a star exist in a place where space itself was not supposed to be? The answer to that impossible question was both incredibly simple and absolutely devastating to the human ego. Space did not end where Harlow Shapley claimed it did. The boundaries of the universe were not drawn at the edges of the Milky Way. Edwin Hubble's measurement of the Andromeda Nebula forced the scientific community to accept a humbling reality. Heber Curtis had been right all along. Andromeda was an entirely separate galaxy, an independent island universe floating in an ocean much larger than anyone had ever dared to imagine. Our massive, all-encompassing Milky Way was instantly demoted to being just one localized galaxy among countless others. In the decades that followed this revelation, cosmologists scrambled to rebuild their understanding of reality. They constructed a new, elegant model to replace the broken one. This new framework was built heavily upon something called the cosmological principle. The core idea was comforting in its own way. If you zoom out far enough, the universe is perfectly uniform and homogeneous. It was envisioned as a smooth, evenly mixed soup of matter. Sure, there were localized clumps like stars, galaxies, and even clusters of galaxies, but at the grandest scales, every patch of the universe was supposed to look exactly like every other patch. There was a strict mathematical limit to how large a cosmic structure could be. Because the universe was born 13.8 billion years ago in the Big Bang, gravity had a strictly limited amount of time to pull matter together. Therefore, the new dogma dictated that no structure in the universe could possibly exceed a few 100 million light-years across. Anything larger would violate the fundamental laws of physics and time. For a long while, this neat homogeneous model held firm, But just like the Milky Way-centric model before it, the smooth universe model was destined to crack under the weight of better observations. The first major fracture appeared in 2003 at Princeton University. A team led by astronomers Richard Gott and Mario Urich was analyzing the first waves of data from the Sloan Digital Sky Survey. This was an incredibly ambitious project aimed at creating a detailed three-dimensional map of the cosmos. The researchers were not looking through eyepieces on freezing mountains. They were crunching massive datasets collected by automated telescopes, analyzing the redshift of galaxies to plot their exact coordinates in three-dimensional space. When Gott and Urich plotted their map, a monstrous anomaly appeared on their screens. It was a dense, continuous filament of galaxies tightly bound together by gravity. They named it the Sloan Great Wall. The problem was not its existence, but its sheer, terrifying scale. The wall stretched for an estimated 1,370,000,000 light-years in length. It was a scale that defied comprehension. According to the strict rules of the cosmological principle, this structure was too big to exist. The age of the universe simply did not provide enough time for gravity to drag that much material across that much empty space to form a coherent wall. Some desperate physicists tried to downplay the crisis, arguing that the Sloan Great Wall was not a real, gravitationally bound structure, but merely a random visual alignment of galaxies, a cosmic optical illusion. They fought to keep the homogeneous model alive, but 10 years later, in 2013, the final nail was driven into the coffin of the smooth universe. A team led by István Horváth at the National University of Public Service in Hungary was mapping the universe using a completely different method. Instead of looking for galaxies directly, Horváth's team used data from the Swift and Fermi space telescopes to track gamma-ray bursts. These bursts are the most violent explosions in the cosmos, usually marking the catastrophic deaths of massive stars. Because these massive stars only form in areas densely packed with matter, tracking the explosions allowed the team to map the hidden scaffolding of the universe. What the space telescopes revealed was a structure that made the Sloan Great Wall look like a minor speed bump. In the direction of the constellations Hercules and Corona Borealis, the team detected a massive, dense concentration of gamma-ray bursts. When they calculated the size of the underlying matter creating these explosions, the math returned a number that broke modern cosmology. The structure, now known as the Hercules-Corona Borealis Great Wall, was roughly 10 billion light-years across. This was not a minor anomaly. It was an existential crisis for astrophysics. A structure spanning 10 billion light-years covers more than 10% of the entire observable universe. It is a physical impossibility under the Standard Model. In the 13.8 billion years since the Big Bang, light itself has barely had enough time to cross that distance, let alone allow gravity to slowly orchestrate a web of galaxies on that scale. The universe was not a smooth, uniform soup. It was a jagged, deeply disproportionate web containing structures that defied time itself. As if the discovery of impossible structures was not enough, the actual number of galaxies filling this jagged web was about to undergo a radical revision. In 2016, an astronomer named Christopher Consolis from the University of Nottingham published a study that shattered our senses of the cosmos. Consolis and his team took the deepest, most sensitive images ever captured by the Hubble Space Telescope and applied complex mathematical modeling to them. They were looking deep into the past, analyzing the volume of galaxies at different redshift epochs, reaching almost all the way back to the cosmic dark ages. The team realized that the galaxies we could actually see were only the tip of a cosmic iceberg. By calculating the theoretical clustering of dark matter halos, Consolis extrapolated that for every large visible galaxy, there had to be hundreds of smaller, incredibly faint dwarf galaxies that our telescopes simply could not detect. When the final extrapolation was published, the estimated number of galaxies in the observable universe jumped from a previously accepted 200 billion to an incomprehensible 2 trillion galaxies. This claim immediately triggered a fierce debate in the astronomy community. Researchers like Mark Postman and Todd Lauer argued back, pointing out that measurements of the optical background light of deep space, taken by the New Horizons spacecraft far beyond Pluto, did not show the brightness that 2 trillion hidden galaxies should theoretically produce. The scientific community found itself fractured once again, debating whether we were severely underestimating the population of the universe or drastically over-extrapolating from limited data. But regardless of whether the final count is 200 billion or 2 trillion, the fundamental crisis remains. We are looking at a universe filled with an impossible amount of matter, arranged into structures so immensely large that they break the very timeline of cosmic history. If gravity alone hasn't had the time to build these 10 billion light-year walls, and if the visible matter we see is just a fraction of what is actually out there, then what invisible hand is truly holding this colossal architecture together in the dark? Let me pause here for a second. While I was writing the section about the Hercules-Corona Borealis Great Wall, I physically stopped and just stared at the screen. 10 billion light years? We throw these astronomical terms around so casually, but trying to genuinely imagine a single physical structure that takes light itself 10 billion years to cross makes my brain feel like it is short-circuiting. It is genuinely terrifying. Back to it. The historical crises and shattered dogmas are behind us. It is time to stop looking at the history of discovery and start examining the physical machine itself. To truly understand our place in the universe, we have to look closely at the mechanical anatomy of the Milky Way, not as a static painting in the night sky, but as a grinding, functioning, and highly volatile engine. The true boundary of our galaxy is not where the starlight fades into darkness. The Milky Way is encased within an immense, invisible sphere of dark matter known as the virial radius. This unseen halo stretches out to a staggering 900,000 light-years in every direction, making the actual galaxy roughly 10 times larger than the glowing disk of stars we usually picture. But despite this colossal size, the darker matter within this halo is spread incredibly thin. To visualize this, look at a standard ceramic coffee cup sitting on your desk. The total amount of dark matter currently resting inside that cup is equivalent to merely 1/3 of the mass of a single proton. This ghost-like material is constantly passing right through your body, millions of particles every second, yet it is so heavily diluted that it lacks the physical substance to vibrate even a single atom in your skin. Inside this vast, ghostly sphere, the visible matter of our galaxy is organized into a remarkably complex dual-layer system. The first layer is the thin disk, which measures roughly 1,000 light-years in thickness. This is where our solar system resides. You can think of the thin disk as a highly organized, high-speed, multi-lane highway. The relatively young, metal-rich stars here travel in smooth, orderly and mostly flat circular orbits around the galactic center. However, this organized highway is entirely encased within a much thicker shell, aptly named the thick disk, which spans about 3,000 light-years from top to bottom. The thick disk is an ancient relic of the galaxy's violent, turbulent youth 10 billion years ago. The old metal-poor stars here do not follow the rules of the highway. Instead, they plunge above and below the galactic plane in chaotic, steeply angled orbits, resembling a furious swarm of bees buzzing erratically around a central hive. Through the relentless pull of gravity, these two massive rotating wheels constantly drag, pull, and balance one another to keep the galaxy from flying apart. Even within the relatively calm lanes of the thin disk, our solar system is not riding on a perfectly flat track. As the sun drags us around the galactic center on a massive 220 million year orbit, it is also oscillating vertically. Imagine riding a carved wooden horse on a gigantic cosmic carousel. As the carousel turns, the horse slowly rises and falls. Right now, our solar system is positioned about 65 light-years above the galactic equator, and we are still slowly climbing upward toward the peak of our current wave. It takes roughly 30 to 33 million years to complete one full up and down oscillation. Some theoretical models suggest that this vertical bobbing is not just a harmless ride. Every time we plunge through the dense, gravity-heavy midplane of the galaxy, the gravitational disturbance shakes the icy comets resting in the Oort cloud at the edge of our solar system. This periodic shaking might send swarms of comets plunging inward toward Earth, a cycle that ominously aligns with some of our planet's historical mass extinctions. At the very heart of this cosmic carousel lies the engine that drives it, the central galactic bar. This is a solid, straight structure of densely packed stars measuring 27,000 light-years in length, positioned at a sharp 27-degree angle to our line of sight. This bar is not merely a structural shape, it is an active, functioning machine. It operates almost exactly like an industrial centrifuge pump or a massive rotating valve. As cold hydrogen gas drifts through the spiral arms, it gets caught in the gravitational vortex of this rotating bar. The bar then actively funnels and forces this gas inward, pumping it directly into the intensely crowded star-forming regions at the absolute core. Without this continuous mechanical pumping action to deliver fresh fuel, the center of the Milky Way would have burned through its gas supplies, exhausted its star formation, and faded into cold darkness billions of years ago. This central pump directs its material right to the doorstep of the supermassive black hole anchoring our galaxy, Sagittarius A star. But when astronomers measure the anatomy of this core, they find a glaring anomaly. The central black hole weighs in at roughly 4 million solar masses, while the dense bulge of stars immediately surrounding it holds about 20 billion solar masses. If we calculate the ratio, the black hole makes up just 0.2% of the central mass. To put this in perspective, imagine a galaxy as a peach. The stars are the soft flesh, and the central black hole is the hard pit. According to the standard mathematical rules that govern the growth of galaxies, a peach the size of the Milky Way should have a pit, weighing at least 30 million solar masses. Instead, our core is strangely undersized. This suggests that the Milky Way was a remarkably quiet, inactive galaxy in its early days, essentially going on a strict cosmic diet while other galaxies gorged on gas and merged violently. However, this peaceful, quiet existence is racing toward a catastrophic end. Our galaxy is gravitationally locked in a fatal embrace with the Andromeda Galaxy. Current measurements confirm that Andromeda is hurtling directly toward us at an astonishing 110 kilometers per second. But high speed does not guarantee a collision. The sideways lateral motion is the true deciding factor. In 2012, painstaking measurements revealed that Andromeda's sideways velocity is incredibly small, merely 17 kilometers per second. Picture two heavy billiard balls rolling across a vast green felt table. If they are moving fast but have almost zero sideways drift relative to one another, there is no chance they will simply graze past each other. The geometry guarantees a devastating direct hit. In roughly 4 billion years, these two colossal structures will smash together head-on. As if an impending collision wasn't enough, we're also dealing with structural sabotage from our closest companions. The Large and Small Magellanic Clouds were long thought to be loyal satellite galaxies, safely orbiting us in stable, predictable paths. But recent velocity data has proven this completely wrong. They are moving far too fast to be in a stable orbit. They are rogue, nomadic dwarf galaxies making their very first, highly disruptive plunge past the Milky Way. And they are already leaving scars. The sheer gravitational wake of these two interlopers is aggressively pulling on the outer edges of our galaxy's hydrogen disk. They are bending and warping the edges upwards on one side and downwards on the other, exactly like a vinyl music record that has been left in a hot car and melted completely out of shape. Even the empty space we are traveling through is hostile. Right next door to our galactic neighborhood sits the local void, an unimaginably vast, desolate stretch of nothingness, roughly 150 million light-years across. While empty space technically has no pushing force, the accelerating expansion of the universe changes the rules. In regions filled with galaxies, gravity fights back against the expansion, acting as a brake. But inside the local void, there is no matter to pull back. The space expands violently and unchecked, acting like the surface of a rapidly inflating rubber balloon that forcefully sweeps dust particles away from its center. Because we are perched on the very edge of this massive void, its unchecked expansion is actively blowing our entire galactic neighborhood away at an incredible 260 kilometers per second. As we are swept away, the space between us and other galaxies is not entirely empty. It is filled with a sprawling invisible web of plasma known as the warm-hot intergalactic medium. This gas is heated to an unimaginable 10 million Kelvin. You might assume that plunging into 10 million degree gas would instantly incinerate you. However, this medium is spread so unbelievably thin that there is, on average, only a single proton per cubic meter. If you could miraculously step out of a spacecraft into this intergalactic web without a spacesuit, you would not burn at all. Because there are virtually no physical particles to transfer that immense thermal energy to your skin, you would simply, instantly freeze to death in the terrifying isolation of the deep void. If the mechanical anatomy of our galaxy is this fragile, constantly warped by passing dwarfs, pushed by expanding voids, and locked on a fatal collision course, How does it maintain its highly ordered spinning spiral structure without instantly tearing itself to pieces? The reason our galaxy does not instantly rip itself apart under the violent forces of its own rotation is deeply counterintuitive. According to standard Newtonian physics, the further a planet or a star is from the center of gravity, the slower it should orbit. This holds perfectly true for our solar system, but spiral galaxies completely defy this logic. The stars on the extreme outer edges of the Milky Way are tearing through space at the exact same terrifying speeds as the stars near the center, moving at hundreds of kilometers per second. With that much centrifugal force, the outer arms should violently fling themselves out into the void, shredding the galaxy instantly. The fact that this does not happen was a massive anomaly until astronomers Sandra Faber and John Gallagher confirmed the solution in 1978. The visible stars do not possess nearly enough gravity to hold themselves together. They are saved entirely by the invisible grip of the dark matter halo. 85% of the galaxy's mass is dark matter. The brilliant glowing galaxy we see is nothing more than a sprinkling of shiny glitter, embedded inside an overwhelmingly massive invisible lump of cosmic clay. This realization forces us to confront how deeply our intuition fails us when dealing with the cosmos. We carry a heavy baggage of myths, taught to us by decades of pop culture, old textbooks, and science fiction movies. For example, consider the impending collision with the Andromeda Galaxy that we explored earlier. When we hear the word collision, our minds immediately conjure up Hollywood-style apocalyptic imagery. We picture a chaotic, fiery apocalypse where billions of stars smash into one another in a catastrophic cosmic explosion. This is a complete myth. The reality, as calculated by Thomas Cox and Abraham Loeb at the Harvard-Smithsonian Center for Astrophysics, is profoundly different. The sheer volume of empty space between the stars is so unfathomably vast that the physical collision of two stars during a galactic merger is almost mathematically impossible. The probability is roughly 1 in a trillion. Cox and Loeb compared it to two people standing hundreds of miles apart, each throwing a single handful of sand into the air and expecting two grains to strike each other mid-flight. When the Milky Way and Andromeda finally meet, they will not crash. They will pass through each other completely silently, like two ghosts intertwining, before gravity slowly pulls them into a new, stable orbit. Our intuition fails us just as badly when we look at the very center of our galaxy. There is a deeply ingrained myth that the supermassive black hole at the core, Sagittarius A star, is a cosmic vacuum cleaner. We falsely assume that it is only a matter of time before it inevitably sucks in every single star, including our Sun, devouring the entire galaxy. This misconception is largely driven by the terrifying etymology of the word black hole itself, framing it as a bottomless, hungry pit. However, the meticulous observations of Reinhard Genzel and his team have proven this to be entirely false. The direct gravitational dominance of the central black hole, the area where its pull is the absolute master, is an unbelievably tiny sphere measuring just 10 light-years across. Beyond that minuscule radius, the galaxy is held together by the collective gravity of billions of stars in the dark matter halo, not the black hole. If you were to magically erase Sagittarius A star from existence today, the rest of the 100,000 light-year-wide galaxy, including our solar system, would continue orbiting as if absolutely nothing had happened. But perhaps the most profound myths we harbor are about the universe itself. When we hear the term Big Bang, we naturally picture a conventional explosion. We imagine a bomb going off at a specific center point, expanding outward to fill a pre-existing dark, empty room. This creates the persistent illusion that the universe has an edge, and that it is expanding into something else. This is fundamentally incorrect. In 1927, Georges Lemaitre helped us realize that space itself is expanding. There is no center, and there is no outside room. To understand this, astronomer Charles Lineweaver uses the brilliant analogy of a loaf of raisin bread baking in an oven. As the dough bakes and swells, every raisin moves away from every other raisin. The raisins themselves are not swimming through the dough between them is physically expanding. In this analogy, the raisins are galaxies and the dough is space itself. Because the expansion happens everywhere at once, every single raisin perceives itself to be the exact center of the expansion. There is no central point of the Big Bang because at the very beginning, every point in the universe was squeezed into that single origin. The very spot where you are sitting right now is the exact center of the Big Bang, and so is a galaxy 10 billion light-years away. This expanding dough analogy also destroys another famous myth, the idea that distant galaxies are breaking Einstein's absolute speed limit. We observe galaxies near the cosmic horizon moving away from us much faster than the speed of light. Many people assume this disproves the theory of relativity. However, the galaxies are not moving through space faster than light. The space between us is simply stretching. There is absolutely no speed limit on how fast the dough of space can expand. This relentless stretching also shatters our intuitive grasp of time and distance, leading to the ultimate cosmic misunderstanding. Because we know the universe is 13.8 billion years old, simple logic suggests that light has only had 13.8 billion years to travel. Therefore, the absolute limit of the observable universe should be a sphere with a radius of 13.8 billion light-years. This seems like common sense, but it completely ignores the expanding dough. When we look at a galaxy whose light took 10 billion years to reach us, we're not looking at an object that is currently 10 billion light-years away. As astronomer Edward Wright's cosmological calculators demonstrate, when that ancient light first left the galaxy, it was actually only about 5.5 billion light-years away from us. But as the light traveled toward our telescopes, the space it was crossing was aggressively expanding. The light was forced to act like a swimmer fighting against a rapidly accelerating river. By the time the exhausted light finally reached our eyes, the relentless expansion of the universe had carried the original galaxy far, far away. When astrophysicists like Richard Gott calculate this co-moving distance, factoring in the stretching of space over time, the true scale of our reality is revealed. The edge of the observable universe is not 13.8 billion light-years away. The physical boundaries of the light we can see have been pushed out to a staggering radius of 46.5 billion light-years, giving us a total observable diameter of 93 billion light-years. If everything our daily intuition tells us about collisions, gravity, speed, and distance breaks down so completely at these scales, and if the visible horizon has been stretched to 93 billion light-years, we must inevitably ask, what exactly lies beyond that absolute boundary of light? To understand what lies beyond the absolute boundary of light and how our local structure manages to stay intact, we must map the physical scaffolding of the cosmos. As we zoom out from our solar system, we discover that the universe is not just a random scattering of stars and galaxies. It is a highly interconnected, intricately balanced physical structure. Every layer is bound to the next, separated by invisible borders and terrifying voids. The ground beneath us is shifting, but it is shifting within a deeply organized architecture. Right here at home, our solar system is currently sailing through a specialized pocket of space known as the local bubble. Roughly 14 million years ago, a chain reaction of massive supernova explosions ripped through our neighborhood. The shockwaves acted like a fleet of cosmic snowplows, violently pushing the dense interstellar gas outward. Today, we sit in the warm, hollowed-out cavity left behind by those explosions. The local bubble is about 1,000 light-years across, and our sun blindly drifted into it about 5 million years ago. As we travel through this cleared-out space, we are also surfing a colossal structure known as the Radcliffe Wave. For decades, astronomers thought the gas clouds near us were disconnected rings, but three-dimensional mapping proved they form a single, continuous 9,000 light-year-long filament. This structure undulates precisely like a massive sine wave rolling across an ocean, dipping 500 light-years below the galactic plane and cresting 500 light-years above it. We are currently passing right through the heart of one of its fading ripples. But when we attempt to look past these immediate local waves, to see the grander structure pulling at us, we hit a literal wall. Our own Milky Way blinds us. The thick, dusty disk of our galaxy stretches across the sky, physically blocking our view of the universe behind it. For a long time, astronomers called this the zone of avoidance, assuming the dark patches were simply empty regions of space. It casts a heavy optical shadow over 10 to 20% of the entire sky. To pierce through this blinding curtain, researchers had to abandon visible light and use massive radio telescopes tuned to the 21-centimeter wavelength of cold hydrogen. Radio waves slip through the thick dust uninterrupted. When astronomers finally looked through the zone of avoidance, they were stunned to find entirely hidden continents of galaxies including the mysterious Great Attractor, actively pulling our entire galactic neighborhood toward them. As we map the path toward these distant attractors, we realize that the space between galaxies is not the empty vacuum we once imagined. Our Milky Way belongs to the Virgo cluster, a massive gathering of thousands of galaxies. If you were to weigh the cluster, you might assume the mass comes from the brilliant visible stars. In reality, the space between the galaxies is filled with a boiling invisible plasma known as the intracluster medium. This X-ray emitting gas is heated to a staggering 30 million Kelvin by the friction of falling galaxies, supernova shockwaves, and the violent jets expelled by supermassive black holes. The total mass of this burning plasma is 5 to 10 times heavier than all the stars in the Virgo cluster combined. The galaxies we see are merely tiny islands floating in a suffocating invisible ocean of superheated fog. Within our local corner of this fog, there is a strict gravitational boundary that dictates our ultimate fate. In the 2.5 million light-years of dark space separating the Milky Way from Andromeda, there exists an invisible critical threshold, a cosmic watershed line. Because Andromeda is significantly heavier than the Milky Way, the gravitational equilibrium point is not perfectly in the middle. It sits exactly 1 million light-years away from our Sun. If you were to fly a spaceship past this exact boundary and cut the engines, you would never fall back to the Milky Way. You would be permanently caught in Andromeda's inescapable pull, slowly accelerating toward a fiery demise in its core. It is the absolute point of no return for our galactic neighborhood. Beyond this watershed, the true jagged scaffolding of the universe reveals itself in the form of cosmic filaments and great walls. In 1989, astronomers Margaret Geller and John Ushra mapped a structure that sent shockwaves through the physics community, the Center for Astrophysics Great Wall. This structure is a staggering 500 million light-years long and 200 million light-years wide, but it is remarkably thin, measuring only 16 million light-years in depth. It resembles a colossal, crumpled sheet of paper drifting in the void. Its entire delicate structure is pinned together and held taut by two incredibly dense, massive galactic clusters at either end, acting like heavy nails driven into a wall. Even more striking is the Pisces-Perseus Supercluster, a solid filament of galaxies stretching continuously for 300 million light-years. But in the cosmos, every extreme density demands an equally extreme emptiness. Right next to this blindingly crowded wall of galaxies lies the Taurus Void, a desolate spherical wasteland roughly 100 million light-years across. The void is so perfectly empty that not a single galaxy resides inside it. All the matter has been aggressively swept to the edges, creating a terrifying contrast. It is the cosmic equivalent of looking at a densely populated, towering continent dropping instantly into the pitch-black abyss of the Mariana Trench. Curiously, not all voids are completely dead. The terrifying Bhuta's Void, spanning 330 million light-years, contains a highly anomalous feature. Deep within its isolating darkness, astronomers discovered a very thin, delicate tube of about 60 isolated galaxies cutting straight through the center. These galaxies live an entirely quarantined existence. Because they have no aggressive neighbors to crash into or steal their gas, they have retained massive reservoirs of pristine hydrogen. While galaxies in crowded clusters quickly age, turn red, and die, these isolated tube galaxies continually forge new stars, remaining bright, blue, and eternally young in their absolute solitude. Yet all of these structures, the thin sheets, the towering continents, and the deep trenches, are ultimately chained to an even greater master. The entire local cosmic web, including our own Laniakea supercluster, is being dragged toward the core of the Shapley Supercluster. This core is an apocalyptic melting pot of colliding galaxy clusters. The hot gas alone in this central region possesses the mass of 100 trillion suns. It is so unimaginably massive that its gravity successfully fights back against the accelerating expansion of the universe itself, locking tens of thousands of galaxies into a single, inescapable point. We now have a map of the intricate, fragile, and awe-inspiring scaffolding that connects our neighborhood to the vast cosmic web. We understand how the invisible plasma, the towering walls, and the deep voids physically bind the universe together. But as we comprehend the true, staggering scale of these structures spanning hundreds of millions and billions of light-years, we are forced to finally confront the original, terrifying question. Against this overwhelming architecture, how unbelievably small is the Milky Way galaxy really? To answer that question, we must drastically compress our perspective. The observable universe is roughly 93 billion light-years across, harboring an estimated 2 trillion galaxies. If we were to shrink that entire 93 billion light-year volume down to the size of planet Earth, our massive Milky Way galaxy, with its hundreds of billions of stars, its colossal dark matter halo, and the entirety of human history, would be roughly the size of a single red blood cell, floating somewhere in the middle of the Pacific Ocean. That is our true scale. We are not a major load-bearing component of the cosmic architecture. We are a microscopic, nearly irrelevant rounding error. But recognizing our microscopic scale brings us face to face with the most profound paradox in modern astrophysics. It is a paradox that shatters our fundamental intuition about reality, and it begins with an observation so common we never question it: the darkness of the night sky. Consider the terrifying math we have established. The universe contains 2 trillion galaxies, which collectively hold roughly 100 sextillion stars. Logic and common sense dictate a very specific outcome here. Imagine standing right in the center of an infinitely large, incredibly dense forest. If you look horizontally in any direction, your line of sight will eventually hit the wooden trunk of a tree. You will not see any open horizon. The night sky should operate exactly the same way. With 100 sextillion stars scattered across the void, no matter where you point a telescope or your naked eye, your line of sight must eventually land on the fiery surface of a distant star. According to the strict laws of optics, surface brightness does not diminish with distance. A star 10 billion light-years away looks physically smaller, but the light that does reach your eye is just as intensely bright as the surface of our sun. Therefore, the night sky should not be a canvas of black painted with tiny pinpricks of light. The entire sky, at every single point, should be blazing with the blinding, scorching brightness of a stellar surface. The night should be as white and terrifyingly hot as staring directly into the sun, but it is not. The sky above us is a freezing, pitch-black abyss. Why? Our intuition fails us because we instinctively assume the universe is infinite in age and completely static. The blackness we see is the ultimate physical proof that the universe has a finite age of 13.8 billion years. The light from the most distant trees in the forest simply has not had enough time to reach us yet. Furthermore, the expanding dough of space stretches the light that is traveling toward us, pulling it down into invisible infrared frequencies. The darkness of the night sky is essentially a colossal optical illusion created by the limits of time and the stretching of space. However, when astronomers use highly sensitive microwave telescopes to peer deeply into that dark illusion, they uncover a second, far more severe paradox that appears to break the fundamental laws of thermodynamics. When they measure the cosmic microwave background radiation, the faint lingering heat signature left over from the Big Bang, they look at the extreme eastern edge of the observable horizon, roughly 46.5 billion light-years away. They measure the temperature there. It is exactly 2.7 Kelvin. Then, they turn the telescope to the extreme western edge, looking in the completely opposite direction, another 46.5 billion light-years away. The temperature there is also exactly 2.7 Kelvin. In fact, these two extreme edges match perfectly down to the 5th decimal place. Our everyday common sense tells us this level of synchronization is physically impossible. The total distance between those two opposing edges is 93 billion light-years, yet the universe itself is only 13.8 billion years old. Because absolutely nothing can travel faster than the speed of light, these two extreme edges of the universe have never had the physical time to exchange a single photon, a single unit of heat, or a single piece of information. They are completely isolated from one another. To understand how absurd this harmony is, imagine pouring a cup of boiling water inside a sealed room in Tokyo, and simultaneously placing a block of solid ice inside a sealed room in New York. Without any physical contact, without any air flowing between them, both the water and the ice instantly equalize to the exact same temperature down to the 5th decimal place. In physics, for temperatures to equalize, materials must physically interact. Yet the two opposing extremes of our universe are perfectly synchronized without ever having the physical time to touch. This impossible synchronization is known as the horizon problem. This impossible harmony is compounded by yet another terrifying precision. Our universe exists in a state of nearly perfect spatial flatness. The outward expansion of space and the inward pull of gravity are balanced on a microscopic razor's edge. For the universe to appear this geometrically flat today, the initial conditions immediately following the Big Bang had to be tuned with an accuracy of 1 part in 10 to the power of 50. That is a 1 followed by 50 zeros. If the initial density of the universe had deviated by even a single fraction of a trillionth of a percent, the delicate balance would have catastrophically failed. A fraction more gravity, and the universe would have collapsed back in on itself billions of years ago in a crushing big crunch. A fraction less gravity, and everything would have flown apart so violently that no galaxy, no star, and no planet could have ever formed. We exist on a mathematical knife edge that basic intuition says should be statistically impossible to achieve by mere chance. And if this perfectly tuned, perfectly synchronized, microscopic existence was not enough to induce complete cosmic vertigo, there is one final anomaly that leaves astrophysicists staring at their data in absolute disbelief. Our Milky Way, along with hundreds of massive galaxy clusters surrounding us, is not just drifting randomly through the void. We are being actively pulled. Measurements of the cosmic microwave background reveal that our entire local region of the universe is caught in a massive river of gravity known as the dark flow. We're all moving together, plunging toward a specific point between the constellations of Centaurus and Vela, at an incredible unified speed of roughly 600 kilometers per second. Our intuition tells us that if an unseen force is pulling thousands of massive galaxies with that much violent gravitational power, there must be an unimaginably heavy structure, a supercluster of unprecedented scale, acting as the anchor. But when astronomers point their most powerful telescopes in the direction of the flow, searching the sky all the way out to the absolute edge of the 46.5 billion light-year horizon, they find absolutely nothing. There is no structure massive enough to cause this violent current. The source of the gravity dragging us through space does not exist within our observable universe. We are a microscopic speck in a vast web of 2 trillion galaxies, perfectly tuned to an impossible decimal point, synchronized across a 93 billion light-year void without ever communicating, and we are being violently dragged into the dark by a monstrous gravitational force that technically does not exist within our reality. If the strict laws of physics demand that cause and effect are bound by the speed of light, and the boundaries of our observable universe are absolute, how can an invisible ghost outside of our known universe be pulling us toward the edge? The answer to how these impossible synchronization problems and ghostly gravitational pulls exist does not require us to abandon the laws of physics. Instead, it requires us to completely surrender our concept of scale. The solution to this terrifying cosmic puzzle brings with it a profound, chilling sense of awe, because the answer reveals that the 93 billion light-year abyss we have been measuring is not the entire ocean. It is merely a single droplet. To understand how the extreme eastern and western edges of our universe share the exact same temperature down to the 5th decimal place without ever touching, we have to look at a mechanism proposed in 1980 by physicist Alan Guth. It is a mathematical model known as cosmic inflation. The theory suggests that the Big Bang was not a slow, steady expansion of space. Instead, in the unimaginably brief window between 10 to the power of -36 and 10 to the power of -32 seconds after the beginning, space itself underwent a violently aggressive exponential expansion. During that fraction of a microsecond, the fabric of the universe expanded trillions upon trillions of times faster than the speed of light. This violent inflation perfectly solves the horizon problem. The 2 distant edges of the universe that are now separated by 93 billion light-years did not synchronize their temperatures across that massive void. Before inflation triggered, the entire observable universe was smaller than a single proton. The extreme east and the extreme west were intimately connected, physically touching one another in that microscopic state. They shared their heat and equalized perfectly. Then, inflation acted like a cosmic detonator, instantly ripping them apart and scattering them across tens of billions of light-years before they had a chance to drift out of sync. This same violent stretching also solves the terrifying precision of the flatness problem. Imagine taking a deeply wrinkled, crumpled piece of fabric and suddenly pulling the edges outward with the force of a speeding train. The fabric will instantly snap into a perfectly flat, tight surface, ironing out every single wrinkle. Inflation stretched the geometry of space so aggressively that any initial curves, bumps, or density anomalies were instantly ironed out, leaving behind the mathematically flawless, razor-edge flatness we observe today. But if inflation stretched space that violently, it forces us to accept a staggering reality about the dark flow. The 93 billion light-year sphere we call the observable universe is not the whole picture. It is simply the absolute limit of what we can see, bounded by the speed of light. Because inflation pushed the rest of the universe far beyond our optical horizon, the true size of the cosmos is exponentially larger than our observable bubble. The invisible ghost pulling our galaxy at 600 kilometers per second toward the edge is not a ghost at all. It is simply the rest of the universe. There are towering great walls, massive superclusters, and unimaginable cosmic architectures resting silently in the dark just beyond our horizon, applying their massive gravitational weight to our local web. Yet, solving these immediate paradoxes only pushes us into an even deeper, more humbling realization. If inflation can create a universe this vast, how did it manage to create one with the exact, precise balance of dark energy required to allow galaxies to form? Why did the cosmic inflation stop exactly when it did, leaving behind a perfectly tuned vacuum? The answer offered by modern theoretical physics, specifically championed by physicists like Leonard Susskind using the mathematics of string theory, strips away the last remnants of human ego. The mathematics suggest a concept known as the anthropic multiverse, or the string theory landscape. The equations indicate that the process of inflation did not happen just once to create our specific universe. Instead, the geometry of higher dimensions can fold and collapse in roughly 10 to the power of 500 different ways. That is a 1 followed by 500 zeros, a number so incomprehensibly massive that it violently dwarfs the total number of atoms in our entire observable universe. In this model, inflation is eternal, constantly bubbling and spawning new pocket universes, each with its own randomly assigned laws of physics, its own gravity, and its own value of dark energy. Imagine an infinite cosmic casino, where the universe is blindly rolling a trillion-sided die over and over again. The overwhelming majority of these newly born universes are instantly hostile. In most of them, the dark energy is too strong, violently ripping space apart in milliseconds before a single star can ignite. In others, the gravity is too heavy, instantly crushing the newborn universe back into a microscopic point. The reason our universe possesses this terrifyingly perfect balance, the exact flatness, the perfect temperature, the incredibly weak dark energy that allowed the Milky Way to slowly assemble over billions of years, is not because the cosmos was engineered for us. We are simply the survivors of statistical inevitability. Out of 10 to the power of 500 violently uninhabitable voids, we happen to reside in the one incredibly rare, incredibly quiet bubble where the physics accidentally balanced out. If it had not, we simply would not be here to measure it. This is the final, ultimate answer to the question we asked at the very beginning of this journey. We asked, how incredibly small is the Milky Way galaxy really? We mapped the towering structures, the 10 billion light-year walls, and the 93 billion light-year horizon to show that the Milky Way is nothing more than a single red blood cell floating in a cosmic ocean. But now, we must face the ultimate scale. That entire 93 billion light-year ocean, everything we have ever seen, every star, every void, every galaxy, is itself nothing more than a microscopic temporary droplet trapped within an infinitely violent storm of 10 to the power of 500 other universes. The Milky Way's insignificance is absolute. It is a speck of dust inside another speck of dust. But rather than despair, there is a profound, terrifying beauty in this realization. Against an infinite backdrop of chaotic, tearing universes, our fragile microscopic galaxy managed to survive. It held together just long enough and remained quiet enough to allow conscious minds to open their eyes and witness the sheer scale of the storm around them. We have resolved the paradox of our existence by pushing the boundaries of reality out to mathematical infinity. But if our perfectly tuned, observable universe is just one fragile droplet holding its breath in an infinite cosmic storm. How long can this delicate balance possibly last before the droplet finally evaporates? To comprehend how long this delicate balance can last, and to truly grasp the terrifying scale of the rules that govern us, we must abandon abstract numbers and measure the universe using the only metric we intuitively understand: our own human lives. We must tie the cosmic scale to the ticking clock of our everyday existence. Consider the slow, seemingly peaceful passage of an ordinary day. Imagine you are driving your car and a standard 3-minute pop song plays on the radio. During those exact 180 seconds of music, the universe does not sit still. In that brief window, our massive neighbour, the Andromeda Galaxy, hurtles exactly 19,800 kilometers closer to us. By the time the song fades out, a colossal structure containing 1 trillion stars has physically closed the gap between us by a distance greater than the entire diameter of the Earth. The universe is a gigantic, relentlessly grinding clockwork, and we are strapped to its gears. We often pride ourselves on our speed and technological mastery over these gears. The fastest object humanity has ever built is the Parker Solar Probe, designed by NASA to plunge into the atmosphere of the Sun. Using the gravitational whip of planets, it achieves a blistering top speed of roughly 194 kilometers per second. This is hundreds of times faster than a speeding rifle bullet. But if we turn this pinnacle of human engineering toward the stars and attempt to cross our own Milky Way, our pride instantly evaporates. To travel from one edge of our 100,000 light-year-wide galaxy to the other at this absolute maximum human speed, the journey would take exactly 154 million years. If a team of astronauts had launched this probe from the edge of the Milky Way during the Jurassic period, when giant dinosaurs dominated the Earth, it would only just be arriving at the opposite edge today. Humanity's greatest speed limit is the equivalent of a microscopic insect crawling around a single grain of sand on an endless beach. Because our physical speed is so painfully inadequate, we rely on the speed of light to connect us to the cosmos. But even light, the absolute speed limit of reality, is humbled by the macro scale. In 2024, the James Webb Space Telescope captured the faint red glow of a galaxy known as JADES GSEs 14-0. The light from this galaxy took an incomprehensible 13.5 billion years to reach our mirrors. When those photons began their journey, our Sun, our Earth, and the entire disk of the Milky Way did not even exist. To truly feel the weight of that time, we must scale it to human life. If we take a long, full human life of 80 years and play it back to back over and over, you would need to live exactly 168,750,000 consecutive lifetimes to match the time that light spent traveling through the cold dark. The entire recorded history of human civilization, every empire, every war, every invention fits into the final few seconds of that epic voyage. As that ancient light traveled through the expanding dough of space, it was subjected to immense physical stretching. When the first cosmic microwave background photons were released shortly after the Big Bang, they were incredibly energetic, glowing with a bright visible heat. But as they traveled for 13.8 billion years, the relentless expansion of the universe physically stretched their wavelengths, much like pulling on a piece of elastic rubber. Today, those waves have been stretched by a factor of 1,100, transforming them from visible light into the weak, invisible microwaves that now wash over the Earth. The sources that emit light across these impossible distances operate on an energy scale that breaks human comprehension. Consider a quasar like J0439, one of the brightest objects ever discovered. A quasar is the violently feeding core of an active galaxy. This single object pours out radiation and heat, with a luminosity equivalent to 600 trillion suns. To visualize this on Earth, you cannot simply look at the sun in our sky. You would have to magically clone our sun 600 trillion times, pack the sky shoulder to shoulder with them, and ignite them all at the exact same millisecond. A single, relatively compact cosmic engine outputs more energy in a few seconds than our sun will generate in its entire multi-billion-year lifespan. What drives such apocalyptic energy? The engines at the heart of these quasars are supermassive black holes. The most massive one ever measured is TON 618. Its weight is currently estimated at a mind-bending 66 billion solar masses. If we want to understand its size, we must drop it onto a map of our own solar system. If you replaced our Sun with TON 618, its event horizon, the boundary beyond which nothing, not even light, can escape, would not just swallow Mercury, Venus, Earth, and Mars. It would instantly devour Jupiter, Saturn, Uranus, Neptune, and Pluto. It would swallow the distant Voyager probes and extend deep into the icy Oort cloud. The diameter of this single black hole is 390 billion kilometers. You could place 40 entire solar systems side by side, end to end, and they would all fit neatly inside the dark sphere of its event horizon. It is an abyss of absolute darkness that dwarfs the entire realm of humanity. Yet, as terrifyingly massive as TON 618 is, it becomes microscopic when we step back to look at the galactic clusters. The Milky Way belongs to the massive Laniakea Supercluster, a structure holding 100,000 galaxies and spanning 520 million light-years. Let us shrink this incomprehensible ocean down to the size of a standard 100-meter football field. If Laniakea is the stadium, then our entire Milky Way galaxy, containing our Sun, TON 618, and hundreds of billions of other stars, would be reduced to a tiny 19mm glass marble sitting quietly on the sideline. Every human who has ever lived, every mountain, every ocean, and every dream is confined to a single invisible speck of dust resting on the surface of that 19mm marble. And while our marble sits on the edge, tens of thousands of other marbles swirl and dance across the field, bound by invisible gravitational threads. But between these densely packed fields of marbles lie the voids. The Botas void is 330 million light-years across. To grasp its emptiness, let us shrink it down to the surface area of the Pacific Ocean. If Botas were the Pacific, the 60 rare, isolated galaxies trapped inside it would be reduced to microscopic millimeter-sized islands. An explorer sailing this ocean would have to travel thousands of kilometers just to find the next microscopic grain of land. If an intelligent civilization evolved on one of those islands, they would look up into a completely pitch-black sky. Until they developed highly advanced telescopes, they would firmly believe that their lonely island was the only object in the entire universe. This brings us to the terrifying realization of how painfully empty the universe actually is. Because we see billions of stars in the night sky, we assume space is crowded. But if we took all the matter in the observable universe, every star, every black hole, every nebula, and put it into a cosmic blender, spreading it out perfectly evenly across the entire volume of space, the resulting density would be chilling. Inside a box measuring 1 cubic meter, you would find, on average, just 5 solitary hydrogen atoms. To understand how empty that is, look at the air in the room you're sitting in right now. A single cubic meter of that air contains 27 quintillion atoms. The average density of the universe is roughly 5 quintillion times emptier than the air you're breathing. We think the universe is crowded only because we happen to live on a freakishly dense, rare clump of matter. In fact, matter itself is a cosmic anomaly. We consider stars and planets to be the main ingredients of reality. But for every single particle of normal matter, every proton and neutron, there are exactly 1 billion photons of light drifting through the void. The universe is not a container of solid objects. It is an overwhelmingly vast, freezing ocean of light in which solid matter exists merely as a rare, highly concentrated impurity. And yet, despite this extreme emptiness, the sheer volume of space means that those rare impurities add up to a horrifying total. Today, astronomers estimate there are 2 trillion galaxies in the observable universe. To comprehend this number, we use the famous sand analogy. If you went to every beach, every desert, and every ocean floor on Earth and counted every single microscopic grain of sand, you would not even come close to the number of stars in the cosmos. To equal the roughly 200 sextillion stars scattered across the universe, you would need to find 10 completely identical Earths, entirely covered in sand, and combine them. Every single grain of sand on those 10 planets represents a burning sun, many with their own worlds, their own sunsets, and their own storms. Finally, to see the ultimate macro scale, we must take the entire 93 billion light-year diameter of the observable universe and crush it down into a sphere you can hold in your hand. Imagine compressing reality until the observable universe is exactly the size of a 10-centimeter grapefruit. At this scale, the massive 100,000 light-year wide Milky Way is violently shrunk down to 100 nanometers. it becomes the exact size of a single coronavirus particle. As you hold that grapefruit in your hand, you are holding a dark sphere containing 2 trillion microscopic viruses floating in the void. And our sun, the bringer of all life on Earth, is just a single atom trapped inside one of those viruses. But the most terrifying aspect of the grapefruit is what lies exactly on its skin. Because of the accelerating expansion of dark energy, the space at the very edge of our 46.5 billion light-year horizon is stretching away from us at a terrifying rate. Calculations show that the boundary is receding at approximately 3.3 times the speed of light. Any galaxy resting on the skin of that grapefruit is being swept away so violently that its light will never ever be able to swim upstream to reach us. It has crossed the absolute horizon of reality, fading into a permanent, unreachable darkness. If humanity is confined to a single atom inside a microscopic virus, surrounded by 2 trillion other viruses, trapped in a grapefruit where the edges are hurtling away faster than light itself, how is it physically possible that we know any of this? Who built the tools capable of measuring the weight of a ghost, the speed of a void, and the exact diameter of an invisible horizon? The answer to that question is the ultimate redemption of our microscopic existence. We may be confined to a single atom on a speck of dust, but the human mind refused to remain blind. Over the past century and accelerating furiously into this very decade, we have engineered an armada of precision machinery to read the invisible rules of the cosmos. When astronomers needed to map the exact speed of the dark energy pushing the universe apart, they did not just build a bigger mirror, they built the Dark Energy Spectroscopic Instrument, or DESI, attached to the 4-meter Mayall telescope in Arizona. DESI operates using a truly revolutionary method. On its focal plane, it houses 5,000 independent microscopic fiber optic robots. In less than 10 seconds, these robotic fibers precisely align themselves to capture the light of 5,000 different galaxies simultaneously. It is like a swarm of highly coordinated mechanical insects sipping light from the deep cosmos. However, DESI has a strict physical limit. It becomes blind when looking at extremely faint dusty galaxies beyond a redshift of 3.5, as its optical design simply cannot collect enough photons from that far back in time. Yet, what it can see has already shattered our assumptions. In April 2024, the DESI collaboration released its first-year data. After years of researchers anxiously waiting in control rooms for the massive data sets to compile, the result was a shockwave. DESI found strong statistical signals that dark energy is not a constant static force. The data suggests that as the universe expands, this invisible pushing force is actually losing power and weakening over time, a revelation that threatens to rewrite the entire standard model of cosmology. To look even deeper into the dark, we deployed the James Webb Space Telescope. Its primary tool for looking into the absolute abyss of the past is the near-infrared camera, known as NIRCam. This instrument is meticulously tuned to capture the severely redshifted light from the cosmic dawn, operating specifically between 0.6 and 5 micrometers. It was this exact instrument that in 2024 captured the faint red smear of the Jades galaxy, born just 290 million years after the Big Bang. But NIRCam is also bound by an absolute physical wall. It cannot look beyond the 5 micrometer wavelength. The reason is a terrifyingly delicate law of thermodynamics. If the camera tried to read longer wavelengths, the incredibly faint residual heat radiating from the telescope's own mirrors and electronics would create a thermal noise that completely drowns out the ancient light. Webb is trapped by its own bodily warmth. While Webb looks deep into time, the European Space Agency launched the Euclid Space Telescope in 2023 to map the invisible architecture of space itself. Euclid does not look for dark matter directly. It looks for the shadows it casts. It uses a method called weak gravitational lensing. As light from distant galaxies passes through the massive invisible clumps of dark matter in the foreground, the intense gravity slightly bends and ovalizes the shapes of those distant galaxies. It is exactly like trying to read a newspaper through the distorted, curved bottom of a glass of water. By measuring these 1% distortions across billions of galaxies, Euclid can draw a map of the invisible scaffolding. Euclid's greatest enemy is our own home. It is physically blinded by the thick, dusty disk of the Milky Way, which completely blocks its ability to resolve the delicate shapes of the galaxies hiding behind it. Yet, in early 2024, Euclid released its first early data and stunned researchers. While mapping the massive Perseus cluster, the telescope's unprecedented precision detected the faint glow of hundreds of thousands of orphaned stars, stars that had been violently ripped away from their home galaxies, doomed to drift forever in the lonely dark voids between the cluster's main galaxies. Down here on Earth, our instruments are just as extreme. Buried 2.5 kilometers deep into the absolute darkness of the Antarctic ice sheet is the IceCube Neutrino Observatory. It is hunting for the most elusive ghosts in the universe, neutrinos fired from the cores of active galaxies. Because these particles almost never interact with matter, millions pass through the Earth completely untouched. IceCube waits for the incredibly rare moment when a high-energy neutrino directly strikes an oxygen atom trapped in the pristine ice. When it hits, it creates a secondary particle that moves through the ice faster than the speed of light and water, leaving behind a brief blue flash of Cherenkov radiation, exactly like a fighter jet creating an acoustic sonic boom. IceCube's physical limit is that it is completely blind to low-energy neutrinos, anything under 10 giga-electron volts. The faint flashes from those weaker impacts simply drown in the background noise of the ice. But in 2023, the IceCube team proudly announced a monumental victory. They detected high-energy neutrinos originating not just from distant quasars, but directly from the dense, chaotic center of our own Milky Way, proving for the first time that our galactic core operates as a massive natural particle accelerator. Perhaps the most delicate of all our machines are the LIGO detectors, designed to feel the actual stretching of space-time. By firing lasers down long vacuum tubes, LIGO measures the gravitational waves created when massive objects like neutron stars collide. These waves allow astronomers to measure the distance to catastrophic cosmic events with absolute precision, offering a brand new way to calculate the expansion of the universe. But LIGO has a frustrating physical blind spot. The instrument is so unimaginably sensitive that it is blinded by the heartbeat of the Earth itself. The crashing of ocean waves on distant shores, the swaying of trees in the wind, and microscopic seismic tremors create a wall of terrestrial noise that completely masks any gravitational wave under the frequency of 10 Hz. Because of this, LIGO can never hear the slow, deep-frequency groans of supermassive black holes merging. It is deafened by the very planet it sits on. To escape the Earth's interference, we go to extremes. The Atacama Large Millimeter Array, or ALMA, consists of 66 massive radio antennas designed to detect the faint microwave signals of cold gas in the early universe. But ALMA's biggest enemy is water vapor in the Earth's atmosphere, which acts like a thick sponge, completely absorbing the delicate microwaves from space. To bypass this blind spot, astronomers were forced to haul these massive dishes up to a breathtaking altitude of 5,000 meters on the Chanantor Plateau in the Chilean Andes, placing them above the suffocating wet blanket of the lower atmosphere. We have placed our machines on the highest, driest deserts. We have buried them in miles of solid ice. We have launched them into the freezing vacuum of space. We have mapped the invisible shadows of dark matter, caught the ancient light of the first dawn, and physically felt the tremors of colliding stars. But if we possess this incredible armada of precision machinery, and if we can measure the universe down to the width of a proton, what terrifying mysteries are still managing to slip completely undetected through our absolute best nets? The fact that mysteries still slip through our nets is not a failure of modern science. It is the very definition of the frontier. Every new instrument we build pushes the darkness back, but the edge of that darkness is where the most profound questions remain entirely open. In astrophysics, we must draw a ruthless, unyielding line between what we know for a fact, what we suspect mathematically, and what keeps cosmologists awake arguing in the middle of the night. Take the mystery of dark matter. The confirmed absolute fact is this: by watching how fast galaxies rotate and how their mass bends the light of objects behind them, we know there is a massive surplus of invisible matter exerting gravity, yet it refuses to interact with any form of light. The leading mathematical hypothesis is that this mass consists of either incredibly heavy particles called WIMPs, or impossibly light quantum fields called axions. However, what is fiercely debated today is whether this dark matter has its own unique physics, whether it collides and interacts with itself using a fifth, entirely unknown fundamental force. Deep under the mountains of Italy, Physicists at the Gran Sasso National Laboratory use the SNONT detector, a massive tank of liquid xenon, waiting for the microscopic flash of light that would occur if a dark particle struck a xenon nucleus. Yet the exact structure of this particle remains undiscovered, dividing the theoretical physics community. An even more terrifying question lies in the ultimate stability of reality itself. The confirmed fact established by the Large Hadron Collider in 2012 with the discovery of the Higgs boson's exact mass is that the energy state of our universe is mathematically metastable. It is not completely locked in its lowest possible energy state. The terrifying hypothesis born from this fact is vacuum decay. Physicists hypothesize that we are resting in a temporary shallow valley of energy. If a massive quantum tunneling event occurs, space could drop into the true absolute bottom of the valley. This would trigger a bubble of true vacuum that expands outward at the speed of light, instantly destroying all atomic bonds and rewriting the laws of physics as it washes over the cosmos. What is hotly debated is the probability of this cosmic apocalypse. While the math suggests it statistically belongs trillions of years in the future, some physicists argue the bubble could have already spawned beyond our cosmic horizon, and because it travels at light speed, we would never see it coming until the exact millisecond it arrived. Finally, there is the question of what lies outside our bubble. The confirmed fact, written into the uniform temperature of the cosmic microwave background, is that our early universe underwent a violent fractional second of hyper-fast inflation. The leading hypothesis, pioneered by physicists like Andre Linde at Stanford, is eternal inflation. This model suggests that once inflation starts in the quantum field, it never entirely stops. It slows down in pockets to create isolated universes like ours, but continues infinitely in the background, spawning an endless ocean of parallel universes. The fierce, unresolved debate centers on a strange anomaly in our microwave sky known as the cold spot. Some researchers argue this massive, unusually cold patch is the physical bruise left behind when a neighboring parallel universe bumped into our expanding bubble. Others vehemently argue it is merely statistical noise, or a completely normal massive void of empty space within our own borders. These open questions define the absolute limit of human knowledge. We build massive observatories to measure the friction of parallel universes and the weight of invisible forces, obsessively searching the absolute edges of reality. But in our desperation to understand the incomprehensible distances of the infinite dark, we often overlook the space closest to home. We casually assume we understand our own cosmic backyard. We do not. If the universe is fundamentally defined by isolating, terrifying emptiness, do we actually comprehend the true massive distances between the planets in our very own solar system? Or is our local neighborhood far emptier than we ever dared to imagine? Open your eyes. You're standing exactly where we began, in the absolute center of a completely empty, pitch-black room. The silence is still pressing against your ears, but you are no longer the same. The darkness around you is no longer just an empty wall, it's a 93 billion light-year abyss, filled with 2 trillion violent galaxies, perfectly balanced on a mathematical razor's edge, and stretching away faster than the speed of light. In the 17th century, the mathematician Blaise Pascal looked up into the night sky and wrote, "The eternal silence of these infinite spaces terrifies me." He felt the crushing weight of human insignificance. He realized that the universe was not a warm, secure cradle built specifically for us. It is a freezing, deafeningly quiet void where our entire planet is nothing more than a microscopic speck of dust caught in an infinite storm. And the terrifying truth of cosmic solipsism tells us that this darkness is only going to grow. Trillions of years from now, as dark energy accelerates, every distant galaxy will be pushed beyond the absolute horizon. The sky will eventually go completely, permanently black. Any civilization born in that distant era will look up and see absolutely nothing. The universe will systematically erase its own history, leaving them entirely alone in the dark. But the silence of these infinite spaces should not terrify you. The physicist John Archibald Wheeler argued a radical, beautiful truth about reality. The universe requires an observer. If the cosmos was just a blinding storm of burning stars, crushing black holes and dead rocks, with no conscious mind to ever witness it, it would have no meaning. Its existence would be mathematically irrelevant. When you look up at the night sky, or when our telescopes catch the faint light of a galaxy from 13 billion years ago, Your act of observation gives the void meaning. You're not just living in the universe. You're the universe waking up, opening its eyes, and trying to understand itself. We are a microscopic rounding error. We are a single red blood cell floating in a raging ocean of multiverses. Yet, we are the only part of the ocean that can think. But as we stand here on our tiny blue rock, proudly mapping the boundaries of reality and measuring the weight of ghosts, a final unshakable question remains. If the cosmos built this unfathomable architecture just to be observed, and if its ultimate fate is to erase all the evidence and fade into absolute eternal blackness, what exactly is it waiting for us to see before the lights finally go out? If you want to continue exploring these absolute frontiers with us, please subscribe to the channel and share your thoughts in the comments below. As you listen to these final words, I want to know where our voices are reaching. Write down exactly where on Earth you are sitting right now and what hour the clock is showing. Our journey into the dark is far from over, because in our next video we will discover that the true distance between planets